Hello everyone. From now on, we are going to study very important topic in our mathematics, which is vector spaces. Now, the upcoming videos associated with it will be most important not only just for your examinations, but also for the fact to understand mathematics, because these chapters are theoretical and we haven't done any theoretical things, especially in mathematics, up to now. So if you can, be it with me, okay? So let's do it. So we are going to understand the topic vector space. So let's see the definition of vector space. A collection of mathematical objects called vectors that can be added together and multiplied by a scalar is called a vector space. So the defining property of this vector space is that for any combination of these operations, the result in another vector that stays within the same space must follow two rules. First one is closure under addition and second one is closure under the scalar multiplication. So this means vector space is defined by two axioms. First, the axiom of closure under vector addition, and second one is the axiom of closure under scalar multiple. What does we mean by that? So I have said two things: closure under vector addition and again closure under scalar multiplication. I think you are familiar with both of those topics, both of those words, vector addition as well as the scalar multiplication. Okay, so if you see the general concept of multiplication by multiplication by scalar. So let's suppose a scalar. Let's suppose this k is a scalar. Okay, and let's suppose we have a vector. Now, vector can be one-dimensional, two-dimensional, three-dimensional, or four or five or nth dimensional. Let's suppose a nth dimensional vector. Let's suppose V goes from V1, V2, V3 all the way to Vn. What do you think would be the result if we multiply it with a scalar k? Now it is obvious this k is a scalar multiplication. K is a scalar, so this will multiply each of these vectors, and the resulting shape k times v would be k v1, k v2, k v3, so on up to k vn. So this is the property of scalar multiplication. Scalar multiplication. Now, multiplication. Now, let's see the vector addition part. So we know, let's suppose the same vector. Let's suppose we have the same vector, but now instead of a scalar, we have some another vector too. For example, we have a w vector, which is actually again the nth dimensional vector. If we have these, let's suppose w1 vector, w2 vector, w3 vector, all the way up to wn vector. I should put vector sign over their head. So if we have these two vectors, what do you think? this will be. Again, if you have done any algebra in your life, you would be pretty familiar with these things. You will simply add each of these components of the vector and write them as independent individual vectors inside this vector or in this set. Okay, so it will be v2 plus w2, v3 plus w3 plus all the way, not plus, but all the way up to vn plus wn. You have seen here two different things. First, you have seen that whenever you take a vector, actually it's an n-dimensional vector, and typically we don't denote it with set. We use a parenthesis in this way. Okay, we use this parenthesis, and when we have this vector v, now this v vector is actually an nth dimensional vector which is holding n of such v1, v2, v3. Okay, so again we've seen that whenever we add this vector to another vector which is actually the same length of the same dimension, then we have seen that the addition will also yield a vector of the same dimension. Okay. The second thing that we see, that you have seen, is whenever you have a vector and you multiply it with k, which is a scalar, then again it gives the vector of the same dimension. So, what is going on here? So it turns out that if we define something, let's suppose E to be anything, okay? If we define E to be anything, and if it is a case that V, W are the part of these E, then the results the result of adding these and multiplying this vector or this vector with any constant, not constant, sorry, but scalar, has to be the part of E, has to be the part of E. So what I mean is, if we define E to be something, okay, if we define E and we have V, W, and it turns out that V and W are part of this, then if we add these V and W and if we multiply scalars with V and W individually, then it turns out that those things, those operations we did, the result of those operations are also the part of E. If we define that quantity E, then that quantity E is called to be the vector space. Okay, so this is what a vector space is. Vector space. So we have understood the basic thing and basic axioms of a vector space. So we have two properties, vector addition and scalar multiplication. So let's see these two properties one by one. So let's suppose, vector addition. So if we have a vector space, you can think of vector space as anything. Since it's a vector V, we can think of it as a vector V instead of E. It will be more intuitive to us. So let's suppose V. V is a vector space, okay? V is a vector space, and we're talking about its properties. Now, first property is the addition properties or vector addition properties. Now, among that vector addition properties too, there are other sub properties that we're going to do. So let's suppose in vector space, in that vector space, we have two vectors, u and v. If that is the case, then if we add u plus v, then that also belongs to v, right? That this happens for all u and v that belongs to v, no matter what. This is the first property, and this property is known as the closure property. Okay. Now, second property is if we have this u plus v, then since both are the vectors and the vectors are commutative, so we can say this is also commutative, and turns out that this also is a part of vector space. If u and v belongs to v, which is a vector space. For more unambiguous denotation, I would like to use vector arrowhead to suggest that these are actually vectors, but I'm not going to use that in front of on top of vector space. Okay. Now this is called commutative property. The third one is now we add another vector to this vector space. If we have that, then we can write this, and this turns out this also belongs to that vector space, and it is associative, so we can write okay, let me write this. Yeah, so it turns out that this also belongs to vector space for all u, v, w that belongs to v. This is called associative property. The fourth property is identity property. Let's suppose we just have u and we add it with a zero vector. Let's suppose this O, where should I write it? Just imagine that O vector is actually a zero vector, okay? If we add these two vectors, then again we know that this is equal to this and this is equal to u, and since u already belongs to v, that means u plus O or u plus a zero vector also belongs to that vector space, and this is called identity property. And there is a last but interesting property which is called the existence of additive inverse property, which says if we have u that belongs to v and minus u which also belongs to v, so we also have a minus u that belongs to v, then if we add these two vectors, then the result, which is a O vector, that is a zero vector, is again going to be a part of this vector space, and this is called the additive inverse property. And these are the five properties: one, two, three, four, and five properties, which are under the close, which comes under the vector addition properties. Now let's see the vector, sorry, not vector, but multiplication properties. Multiplication properties. First one, let's suppose we have a u. Now again, remember that since even when we are saying it's a multiplication properties, we just mean it's a scalar multiple. Okay, scalar multiplication. So let's suppose we have a scalar. We can consider a scalar to be anything. Let's suppose this to be a. A is not a vector but a scalar. So a is a scalar, and let's suppose u is a vector. If that is the case, then we can write a times u vector also belongs to V for all u belongs to V, and a must be a real number. This is called closure under multiplication. I'm just going to write it as a closure property. Okay. Now the second property is if we have two scalars, let's suppose a and b, which both belong to the real number. If that is the case, then I can write a times b times u, which is also equal to ab times u, and again which is equal to b times au. These all belongs to V if u belongs to V. This is called associative property. Okay, so let's suppose we have two vectors u and v, and we have just one scalar. In that case, we already know that u plus v lies in that vector space, and we multiply a, then it would be distributed both of the vectors, and this thing also belongs to V if for all u v belongs to V. Okay. Now there is a last law which is called identity law or identity property. Identity property. Oh, wait a second. Okay, there is another thing which is called associate. So this is called associative property of vectors. Since a scalar is associated to two vectors, right? Now, sorry, not associated, but actually it's not called associative. Yes, this is associative. Associative, but this is called distributive. So distributive law for vectors. Now again we will have a distribution of scalars. That means if we have two scalars but a single vector, then that vector is also going to distribute to both of the scalars, and this is again going to be a part of or also belongs to the vector space, again for all u belongs to V. Okay. The last property is identity property, and identity property says us identity property that if we have a number which is 1 and it multiplies with a vector u which belongs to the vector space, then is equal to u, right? And this property is true since u already belongs to V. So these are some of the properties which define the very nature of vector space. This is all about vector space. Now let's see something. Okay, so if we have a vector space V, it's a vector space, and from that vector space, now we have already defined the fact that vector space is a set, right? If we take this is a set, for example, V has a lot of things, a lot of vectors. Let's suppose U, V, W, X, Y, and Z. Okay, so let's suppose a vector space, or it's a vector space. Vector space. Now let's suppose, let's take a subset of it, and let's say that to be Y. If we consider this Y a subset of this vector space, then which consists of these three sets, then it turns out in mathematics this Y has its own existence, and its name is vector subspace. Okay, whenever we have a vector space and we take a subset of that vector space, then that vector space actually is called a specific term which is called vector subspace. So you can think of it in the following as the following diagram. Let's suppose this to be a vector space, okay, V. Then you can think of the vector subspace as the box of lesser dimensions in the space. Okay, so this is a visual representation of vector subspace. Mathematically, vector subspace has its own rule. So what is the criteria for a subset to be a vector space? So it doesn't mean that any subspace, so any subset of that large set is going to be a vector subspace. You need to have some certain criteria. Let's write down the criteria. So the criteria, I think I should write the full definition. Yeah. So a non-empty subset vector subspace, or non-empty subset Y in or of vector space V is called to be is a subspace if following conditions are met, and the conditions are: first, 0 vector belongs to Y. Second, the three criterias are 0 vector must belongs to Y. So if we have a Y, then it must contain a 0 set, a 0 vector set. 0 vector is an, or we can say uh, the 0 to be the part of this vector space. Second one is if we have two vectors y1 and y2 in this vector space belonging to this vector space, let's suppose it to be vector space, then in that condition the y1 plus y2 also has to be the part or also has to be inside the set y, and if a is some a is, now there are a lot of other things too. Now a is some scalar, then a times y, which is a scalar multiple of y, must be inside this y2. So in that condition, this y is said to be the subspace, vector subspace. Now you may ask, wait, that are the exact same properties that define the vector space. So why aren't we saying this y to vector space rather than vector subspace? And another question that you can say, you can ask is that if we have the same properties, why are we repeating it again? And the answer to that is, it turns out in mathematics the vector space and vector subspace are exact same things which follows exact same properties, but they are defined on different intervals. They are defined in different domains. So if you remember the previous diagram, I made the vector space to be a bigger box than the smaller vector subspace box. That means the vector space has a larger domain of its existence, and inside that vector space there lies vector subspace. So we can say a statement like all vector space, so all vector subspace are vector spaces, but all vector spaces are not vector subspace. Okay, that was a mouthful, but I think you got the point. So this is about the vector subspace.